Hey, what's going on, everybody? It's episode 6 now, and I'm gonna talk about myself today because I'm egotistical like that, right? Um, this is the 6th episode of our differential equations odyssey, if you will. We have arrived at, exterior differential systems, intrinsic geometry of PDEs and jet bundles. What the heck does that mean? What that means is, we're going to replace partial differential equations themselves, and we're not going to replace them. We're just going to say, actually, partial differential equations are the manifold. Okay, the PDE is the manifold. All right, sounds kind of meta, but just how in everything in math, right? We can just flip it around. If we're just like, yeah, we're looking at the symmetry of this geometry or whatever. It's like, no. Actually, the geometry comes from the symmetry. So it's the same thing. It's like, oh, PDEs and manifolds of PDEs or whatever. It's like tangent spaces. It's like, no, actually the PDE is some coordinates on a manifold. All right, that's what we're doing. Okay, so we're just doing a complete geometric 180. All right, and again, in earlier levels or in earlier episodes, we were hunting for functions that satisfy particular operators, right? But here we're going to flip it. Again, derivatives become coordinates, and the partial differential equations are going to become submanifolds in these vast jet bundles, all right? And let me silence my Discord again. Sorry, I keep forgetting to turn it off. I'm going to crash out. But solutions, these are integral surfaces that are tangent to these hidden contact structures, all right? So that's how I'm going to solve the PDEs that are submanifolds of jet bundles. And, speaking as Jet Bundle himself, yes, that's my handle. We are going to delightfully meta that we are diving into jet bundles today because we're just basically kind of, exploring infinite jet space while you're watching a video from a recursive jet bundle on the YouTube manifold. And if your mind hasn't been blown yet, here's a higher order joke. So if this video prolongs too long, we're going to form a singularity, all right? And if you stick around, we're going to geometrize everything from the overdetermined systems to the universe's shape, okay? And this will crown our geometric term because we're going to build on manifolds and forms. We are going to intrinsicize the PDEs, and we're going to classify via algebra, evolve geometry itself, and I'm going to try to write everything in British spelling today because why not, right? So to geometrize the PDEs, I don't know, it just makes me feel smarter because I'm American. But we put like Z's, whatever, geometrize. Okay, I'm sorry. But we're going to treat X and U, and remember we used to treat them. Sorry, we're not treating them anymore like this, but we traditionally treated partial differential equations as operators on functions, right? So find U such that we have the operator acting on U to be equal to 0. Okay? But think about that. That hides the geometry. Because the overdetermined systems themselves are going to resist this. And singularities will lurk on such a thing where it's just like, operator equals 0, right? Some linear equation. So what we can do is define, or instead of, again, treating X and U and all derivatives on X and U as independent coordinates on jet bundles, the PDE will define submanifolds, and again, the solutions are going to be these surfaces that are compactly embedded within this 3D kind of or 4D or infinite dimensional geometry. So let's look at the one jet space, and this is the most simple one to understand, and it's actually really intuitive. Okay, it's not hard. So if we let some fiber, all right, we're gonna let pi be some fiber bundle where we have some field that is a map onto some space, the jet space. All right, the one jet bundle has coordinates x, u, and p, where p represents the first derivative because it's the one jet space. And a solution is a section of that bundle of this manifold mapping back to the field such that it'll lift a surface that is in the one jet space given by x comma u of x comma u prime of x. All right, you see what happened there? Okay, so we will essentially, again, we're taking fields over space, and the jet 1 has coordinates and first derivatives, and we're lifting u to this within the one jet space. So geometrically, we can think about this that not all surfaces are going to be valid in this space because of some constraint that we're going to require, which is the compactability from a contact form. All right. So the contact form itself, theta, is equal to the exterior or du minus p dx is equal to 0. This is going to be called the Cartan. This is going to encode the Cartan distribution, and a valid solution requires theta be equal to 0. All right, that's it. So geometrically, this defines a field of hyperplanes or contact planes at every point in the jet bundle or the one jet space, and this solution is an integral manifold of the distribution and a surface then that is everywhere tangent to these planes. All right. So for the bundle, this will just be like a one-dimensional manifold, okay, or just like a curve, okay. But for higher order derivatives, because you can take a kth jet space, or an infinite jet space, okay, which allows us to then use Riemann surfaces and all this stuff and genuses, okay, whatever, okay. But you can see where this is going, right? So if we take a first order PDE where we have f of x comma u comma p to be equal to 0, the hypersurface sigma in J1, if we were to solve this is an integral manifold inside of sigma. All right, and if it's overdetermined, we'll need higher jets, but the contact form itself will persist, right? So let's look at a contact field in jet space. That sounds really cool, you know? Come on. Come on. All right. No, that's an invalid curve. Give me a valid curve. Come on. Come on. Sorry, it's kind of a little, I don't know what's going on. My poor computer has like been really slow recently because I have like 500 tabs open. All right. But so what we have here is in a 3D jet space, this is what you're looking at here is a three-dimensional jet space. Again, with x comma u comma p, where p is the first derivative. All right. And let's look at this. So here's u, okay, the function. And then here's x, which is the variable, right, or the coordinate, or whatever. And then here is the derivative with respect to x, right? And we create kind of this like almost, prolonged, like, Lie algebra type thing that we talked about, an episode or two ago. But instead it's in an actual kind of like real, like, space. And it's a sample. These are all sample points here, these planes. These points in the space host these contact planes that are, these like kind of like patches. And we can look at different curves or threads. And the reason why this becomes algebraic is because u is equal to x squared, right? And p is equal to x. And so what happens is if we have, look at this, u equals x squared. Do you see that? U equals x squared. It's a parabola. And then p is equal to x, right? So we're just differentiating with respect to x, okay? Do you see how this could generalize really, really well? And again, this is our, jet bundle that is valid, all right? It's curving, the thread itself is curving along, or the fiber is curving along the tangents. It's very nice. But if we were to violate this, what happens is that if we have an invalid curve, what's going on here is this invalid curve right here is piercing the planes. You see that? It is piercing the planes themselves. They are inconsistent derivatives. And so if you see that the tangency, you'll see that this tangency here is going to enforce holonomic sections. And this is why jet bundles rock. Okay, and not just myself, being egotistical because I rock, but invalid curves are obvious geometrically, and it allows you to prolong your intuition. Okay, so yeah. Anyways, let's generalize, because why not? All right, now that we have a specific use case, now we can see the solution, a valid solution space. All right. Exterior differential systems. And of course, Cartan, generalized this idea to exterior differential systems in 1901. All right, so this is very old. There's nothing new about this. And he took algebra, he took analysis and transformed it into algebra, much like, this was before algebraic geometry, by the way. So if you have some pair on a manifold and I to be the ideal, it's a differential ideal of forms closed under exterior differentiation. We can define that the ideal, and a solution is a submanifold of M such that the pullback will vanish, and so all submanifolds will pull back 0 on the ideal, right? And this is said to be declosed, right? Because if we take the exterior derivative of the ideal, it should be a subset of the ideal, or a submanifold. Okay, all right, or sorry, an algebraic ideal. Okay, so submanifolds. Okay, Cartan-Kahler Theorem. This just tells us existence. Okay, this is an existence theorem, generalized to this space. So we can compute these things called characters, and they kind of just represent the degrees of freedom stepwise. Okay, so S1, S2, and the dimension of the solution space, essentially. Okay, what are the degrees of freedom of the solution space? At each step of this, when we're constructing the integral manifold, if it is analytic and involutive, which just means it's consistent, then the local solutions will exist, and it generalizes Cauchy geometrically, okay, and to geometric systems, and it is said to be overdetermined, and the overdetermined systems are okay if they're involutive. Okay, all right, and the power of this is that we can describe the algebraic obstructions of these solution spaces using Spencer cohomology. And predict solvability itself. Okay, we can predict the solvability of the differential equations itself by algebraizing everything. Okay, now let's apply to geometry. All right, so for a geometry involving partial differential equation, the variable itself becomes the Riemannian metric. Okay, and Perelman proved the Poincare conjecture. And here again, the unknown function is the Riemannian metric itself. So what we need to do is describe the dynamics of this metric. Okay, which is that the rate of change of this metric with respect to time, or the temporal derivative of the metric, is equal to -2 times the Ricci curvature. Okay, or the metric flows that are dictated by that Ricci curvature. So what that means is that we'll have positive shrinks, and spheres will essentially collapse, and negative expands, and we'll get like a heat-like smoothing. Okay, this is essentially what's governing the metric itself. And so if we were to look at singularities in surgery, in finite time, we can get pinches that form, and we can continue to construct surgery on these metric spaces by cutting cut necks and capping spheres and restarting. Okay, and we also need the idea of a canonical neighborhood, which just tells us Perelman's monotonicity to nail the classification of these singularities. All right, so you can read all about that. I'm not going to get too much into it, but that's what the mathematical technology that we're using. Okay, now, and that's a fun word to say, mathematical technology. Sick. Because like I don't know, people are like, yeah, man, I'm so into science and tech, or whatever, and it's like, bro, you're not into tech, or like, you're not into science, bro, you're just into tech. Well, if you're into mathematical tech, I'm into mathematical technology. Okay, so that's what we're doing today. And this would be a dumbbell. Okay, so this is a dumbbell, and we can perform a surgery on the dumbbell with some finite flow time. Okay, so we have, it's a little bit disconnected already, but the dumbbell starts off with nice connected metric space between two balls, two spheres, and they just kind of, you can, as we let them grow and grow and grow, it pinches that in a finite amount of time, and the surgery becomes completely performed by the singularity that is within this. And thank you, Perelman, for proving the Poincare conjecture, because that allows us to define the dynamics of the metric. All right. That's fun. So again, we were able to control the surgery and tame those singularities on those spaces, and prove, uniformization in 3 dimensions. And again, without surgery, it's a topological, without surgery, it's like a topological divorce. Okay, you see that? They're like topologically divorcing each other, and they're, irreconcilable differences in the curvature. Okay, so that's essentially what we're allowed to do here. Now let's talk about gauge theory. All right, so what is gauge theory? This gets thrown around a lot on the internet by people, and I don't think why, until you have a proper understanding of Ricci Flow and exterior differential systems and jet bundles, we really don't have a good foundation to understand what gauge theory really is, right? Now, let's talk about, in particle physics, what the unknown in particle physics is what is said to be a connection, all right, or the vector potential, right? Because the vector potential, if any of you have had any classical field theory, is that the vector potential encodes the Lorentz forces. Oh no, I'm sorry, not the Lorentz forces. Don't cancel me, I'm sorry. The vector potential encodes Gauss's law and Ampere's law, okay? With some scalar potential as well, but like there's a scalar part and then there's a vector part, okay? But the connection is on a principal bundle, right? And if you remember from our previous series, the initial conditions, that principal bundle is really important because, we're putting a gauge structure or a gauge group on it, and the curvature of that determines all of the electromagnetic and weak forces and strong forces and all that stuff. And, the connection is the potential itself. So what we want to do in particle physics is minimize the curvature energy of the connection. All right, that's what the action allows us to do. So if we minimize the integral of, the curvature of some connection for A, right? And of course, this would be for the exterior derivative acting on the curvature or field strength field strength 2 form. All right. The Euler-Lagrange equations are simply the Yang-Mills equation, okay? And so in 4 dimensions, it becomes the curvature form becomes simpler because the solutions to these are said to be mathematical objects called instantons, okay? And the instantons, if you remember from our two episodes ago, I think, solitons, right? What was the property of the solitons? These are, kind of effectively solutions to these nonlinear PDEs that like kind of, like pass through each other and don't scatter, right? So what an instanton is, just think about a topological soliton that is tunneling via some vacuum, okay? On the vacuum. And the topology of these are determined by Chern numbers. And this kind of, again, this allows us to invoke the Atiyah-Singer index theorem, okay? Again, so, and we'll get that BPST, specifically for BPST, we will have, and BPST stands for people's names, but we can get an explicit SU2 instanton, or in other words, a from the particular gauge group that we chose for those connections, or for those principal bundles. The instanton is like this localized energy that will twist at infinity. All right. So that's what the idea of self-duality allows us to express, is that this field itself, okay, this field strength it has this property of self-duality, okay, and the solutions to this equation are the instantons themselves. Okay, so we can look at what exactly is happening with the instanton. All right, so on the left here, you see the gauge field on the sphere. Okay, you have a gauge field on a sphere. That's what you're looking at. And these cones that I'm putting on the sphere, they twist k times, with a Chern number amount of times, right? And what this looks like is, and again, this is called the Chern number. So so they go around once, right? So follow the cones with your eyes, right? So it's kind of hard to do that, but you follow the cones, right? They twist around, one time. Now, if I add further Chern numbers, okay, so let's say 2, then the cones themselves are going to twist around twice, okay? And we can encode this gauge field, or we can encode these gauge twistings at infinity on the sphere, okay? And it's the gauge field on the sphere at infinity, okay? And on the right here is the log energy density. And so if the larger if there's more twists, then there's these ideas of multi-instantons. So let me put a bunch of twists here. And as we scale the instanton, we can get the field strength from it, or the curvature 2 form. And as you can see, the Chern number isn't really changing the energy density, and but again, it peaks at the center and decays here. And so we're in this kind of this is important because of the non-perturbative quantum field theory effects in the vacuum structure. And so we really are able to have a Chern class of kind of our own by watching these instantons. Okay, so now we can go fully nonlinear. Okay, because there's still an instance of linearity that we're assuming here for the curvature 2 form. Okay, now what's next? The Monge-Ampere allows us to finally describe fully nonlinear partial differential equations. And this is where the highest derivatives are wrapped in these nonlinear functions. So we have an equation here. All right, what does this look like? This is the determinant that describes a Hessian determinant. And it is elliptic, or it is said to be elliptic, only for some convex u. Okay, so this equation is only elliptic if u is convex itself, and this is a geometric constraint, right? And because it's a constraint on the shape of the solution itself and not just its smoothness. Okay, so again, so what this allows us to do is describe the idea of regularity, because smoothness inherently is this tricky thing, right? We know this from the very first episode of the Riccati equation, right, where we solve an ODE, in some linear fashion, but because of some artifacts of the coordinate system that we were using, the Riccati has singularities or finite time blowups, right? And so in the same way, smoothness is tricky because in Yao's estimates in 1978 estimated bound derivatives, which enable the idea of a continuity method of allowing us to get solutions that are independent of smoothness itself, all right, of holes. And so let's say we have, and there's this idea of the optimal transport map with Monge-Ampere, which is that if we have some source density and we have a target density, we can actually find a map of optimal transport between both of these. And this is kind of what it looks like here, as you can see. So we're kind of like, allowing this non-linearity to kind of emerge here. All right, so it allows us to optimally transport between two of these densities. Okay, and so again, this source pile, we have this kind of target hole, and then we're interpolating between two of these T itself is like some density morph, and again, these are like arrows that show a transport delta a transport of the of nabla U. Okay, now that's it. So in the real world, you can even think about optimal transport. I mean, this is really important because you can think about optimal transport as like logistics, or I don't know, economics, or like minimal cost shaping type concept. So it's kind of like moving sand, if you will, without like wasting any effort. So it's kind of like, I don't know. So again, PDEs, partial differential equations, are manifolds, and PDEs are jets and contacts, and the jets and contacts will allow us to geometrize the PDEs, and sections of the PDEs are solutions, and EDS, exterior differential systems, algebraize, right? Is that a word? Algebraize existence itself, and for a PDE to actually exist, right? So they algebraize existence, and that's funny to say. And Ricci flows give us topology, right? And then the instantons allow us to gauge these curvature two forms, and the Monge-Ampere transports optimally. Again, this probably wasn't the most perfect rundown of physics and math and everything, and it's kind of condensed in like a really kind of applied way. But I just want to show you guys, I mean, this is just like really beautiful mathematics and beautiful physics, and so, and it's fun. So known coordinates dominate specifically, and the geometry itself, again, we're showing over and over again, geometry rules. So we've really prolonged our series here. Kind of long. This episode's a little long, but again, we have infinite jets now. So what's next is we're gonna talk about micro local analysis in the next, and D modules, sheaves and stuff, categories. Okay, in the next section. So, and solving differential equations with those. All right. So thank you. I will add the notebook after the final episode to GitHub, and you guys can access them there. So like, subscribe, and stay in the Jet Bundle. Goodbye.